There isn't a science around that isn't profoundly influenced by the availability of massive computing power and just greater regular computing power. It's the story of our age. It's not just a story of AI. The idea is to leverage computation to make useful things and to understand the mind. All these things need a lot of computation. It's the fact that computation has become cheaper exponentially for on the order of 100 years and can be expected to continue going that way. It's like doubling every 2 years, now every 18 months. And that keeps happening 18 months after 18 months after 18 months. And it means you double, and things get qualitatively different every decade. And that's happened for a long time, for many decades, and will happen more so in the future. So we have that to look forward to. I think it's what we really should mean when we say the singularity. The singularity is that we have this exploding, it's a slow explosion of computer power, and that is fundamentally changing things.
Hi, I'm Craig Smith, and this is Eye on AI. In this episode, I speak with Richard Sutton, the father of reinforcement learning and professor at the University of Alberta. We discuss his cooperation with John Carmack on Keen, a startup that vows to reach artificial general intelligence by 2030. Richard also talked about the Alberta Plan, his ambitious 5-year research agenda focused on building embodied agents with the capability to learn and plan through interactions with their environment. Sutton provides insights into the current state of progress, new algorithmic developments, and trade-offs between simulated and physical environments in training, and the ultimate goal of creating AGI. I hope you find the conversation as amazing as I did. So why don't you start by introducing yourself? I assume people know who you are. I've had you on the podcast before. But for those new listeners, tell us who you are, where you are, and then we'll talk about the Alberta Plan, which I find pretty exciting.
Thank you, Craig. Well, I'm Richard Sutton. I'm a scientist. I've been studying artificial intelligence for like 45 years, a long time. And I'm up in north at the University of Alberta in Canada, and where I'm a professor in the computing science department, and also I'm a researcher at Keen Technologies, and I got lots of titles and sub roles. But basically, I'm just trying to figure out how the mind works, and I've tried to do it in a very broad, interdisciplinary way, reading all the different thinkers on the subject, and address it from the point of view of psychology and how the brain might work, as well as
I've read
a
number of the recent papers, and I can see this thread developing, and I don't know whether it's just that you're writing more and so the thoughts are more developed in print, or whether they're developing in your mind. But from 2019, when you wrote The Bitter Lesson, you talked about the idea that it's really increasing computation and it's driving a lot of things, a lot of progress.
Mm-hmm.
That kind of coincided with OpenAI's scaling of the transformer model. I talked to Ilya Sutskever, and I asked him whether your essay had triggered their interest in scaling, and he said no, it was coincidental. But first, can we talk about that, about how scaling and the availability of computational resources in Moore's law has driven a lot of what's happened in artificial intelligence research, almost more than novel algorithms?
Well, I think the first thing to be aware of is it's been driving things that are not just artificial intelligence. It's been driving all the sciences and all the engineering developments in the world. There isn't a science around that isn't profoundly influenced by the availability of massive computing power and just greater regular computing power. It's the story of our age. It's not just the story of AI. It's not particularly the story of AI. AI has always known that it needs computation. The idea is to leverage computation to make useful things and to understand the mind. Um, yeah, now it's true that those of us who are interested in connectionist systems or distributed networks, nowadays it's just called neural networks, not a particularly good term, so I always shudder a little bit when I use it. But those of us that have been doing that those of us that have been doing learning think that learning is important for intelligence. All these things need a lot of computation, and so they are limited by the computation available at the time. Okay, so let's be, what is this thing? What is the, so Moore's law? Let's call it Moore's law. It's the fact that computation is becoming more plentiful and cheaper exponentially for on the order of 100 years, and can be expected to continue going that way. So exponentially, that's like doubling every 2 years, now every 18 months. And that keeps happening 18 months after 18 months after 18 months. And it means you double and you double, and things get qualitatively different every decade. And that's happened for a long time, for many decades, and will happen more so in the future. So we have that to look forward to. That will continue having a tremendous influence on everything that's done. On the other hand, it's just normal. It's just what you would expect, and that those of us who worked on AI for a long time have just expect and planned for, and now it's coming, but it's an exponential. So exponentials are self-similar. So that means they look the same at every point in time. Every year, you're doubling in a year and a half, and so it's an explosion, because every exponential is an explosion. It's sort of, I think it's what we really should mean when we say the singularity. The singularity is that we have this exploding. It's a slow explosion of computer power, and that is fundamentally changing things.
Yeah. And I had a really interesting conversation almost a year ago with Aidan Gomez, who was on the team that designed the transformer algorithm at Google. And he now has a startup called Cohere. He's Canadian. And he said an interesting thing that he believes it could have been almost any algorithm. It didn't have to be the transformer. That the community got behind the transformer, poured resources into it, continued to scale it, and it was scalable. I mean, that was important, that it's a scalable architecture, but it didn't have to be the transformer, and that made me think of you, because so transformers, the way he described it at its core, it's a stack of multi-layer perceptrons with attention. You scale it, feed it data, and it does learns to understand language, or at least seems to understand language. But it's got all these obvious limitations. I've been talking a lot over the last couple of years to Jan LeCun about world models, and that to me sounded like a much more exciting direction for general intelligence, because not all intelligence is contained in language, or at least or even less so in human text. And then I see you guys come along with the Alberta Plan, and that sounded even more exciting to me. So, how do you? So the Alberta Plan, you're building. The idea is to build an agent, ultimately an embodied agent, that has a world model, or can create a world model through interactions with its environment. How is that different from LeCun's approach at a very basic level?
Very basic level, good is that they're a very similar idea. It's you look at the parts of his architecture and the parts of the architecture put forth in the Alberta Plan, they line up one for one. We're trying to do the same thing. We're going about it slightly different, and we could talk about that. But I think to focus on the differences might even be to distract from the big message. The big message is that you have to have a goal, and you have to have a model of the world, and then everything is driven by using that model to take action and to plan action at various levels of abstraction in order to achieve the goal. Okay, so to me, this is really what intelligence is: understand the world, use your understanding to get to achieve your goals. I'd like to formulate the goals as a reward, and I'm super comfortable with that. Other people sort of grudgingly accept rewards, even though it seems kind of low level. But it's a natural approach. I think it's something that almost makes more sense to people who aren't steeped in deep learning and supervised learning.
And one thing I found interesting in the roadmap that you've laid out for the Alberta Plan, you start with supervised learning. And why is that? Is it just because it's easy?
Yeah, I guess we do, in a sense, because we want to focus on, well, continual learning continually, which is sort of an obvious thing. What learning means is it's something that goes on at all times. But the first steps, getting continual learning with nonlinear networks, is still challenging, even for supervised learning. And so it's natural to start at the simplest possible case, which involves the fewest other factors, and that's a supervised learning case. Yeah, it's funny. Let me just say a few words about that, because there's sort of been a fight a struggle throughout the decades between supervised learning and reinforcement learning. There's only so much oxygen for learning methods, and all the attention that's paid to supervised learning somewhat detracts from reinforcement learning. And so there's a bit of a friendly competition. And supervised learning has always won the competition because supervised learning is so much more easy to put into practice and for people to use. And it's sort of less ambitious, but it's really important. And really, those of us who do reinforcement learning or try to make whole agent architectures, we are consumers of supervised learning algorithms. We will use them as components of our overall architecture. So we need them, and we can work on them, and we need to structure them for our purposes.
I saw one of your talks. You make a distinction between AI tools and AI agents, and supervised learning falls into the tool category. Can you sort of start and talk about the evolution of the Alberta Plan, and then present to listeners what it is in its simplest form, and that'll give me a structure on which to hang questions.
The Alberta Plan is an attempt to understand intelligence as a primarily a learning phenomenon, something that comes to understand its environment and then drives the environment to achieve goals. So the first step in the Alberta Plan is the structure between the agent, the environment, and their interaction form. The interaction, you're not exchanging states, you're exchanging observations like sensors, visual, touch, auditory. It's all abstract to those particulars, but it's got to be genuine observations and not state, because state we don't really have access to directly. So that, the principles. Number one principle, I'm trying to remember them as I speak. But number one principle is this agent environment interaction is sacrosanct. And number two is that learning or everything is we could say continual. I think we say temporally uniform, temporally symmetric in the Alberta Plan, which means that there are no special phases where you like training and test. There's just life goes on and on. You get rewards, or you don't get the reward you want, and you get your observations. And there's no teacher other than rewards, pains, and pleasures. And maybe I'm not getting the four principles right, but another important point is that you are going to be forming a model, and so you're going to plan. It's both trial and error learning directly from experience, and learning a model, and then planning with the model. Both of these are an important part of intelligence. Okay, so that's the background. And then we outline our 12 steps, and the 12 steps really start with let's have learning that is temporally uniform. Let's have meta learning. Yeah, meta learning, maybe I should stop on that for a moment. Meta learning means learning to learn, not just learning one function, but once you are continually learning, you're learning this and you're learning that, you get many, many experiences learning, and you can get better at learning. You can use those repeated experience with repeatedly learning to make future learning episodes more efficient. So as part of that, you learn representations, you learn features, you learn step sizes. Okay, so continual learning, and then all the algorithms. And once we add meta learning and continual learning, we have to, and supervised learning, then we extend that to reinforcement learning, which involves its own set of issues, to more interesting temporal relationships. And I think like the first 6 steps are crafting the basic algorithms of reinforcement learning, working through them again to be continual and meta. And then we start to bring in the challenging issues like learning off policy and learning models of the world, and then planning. And just to jump to the end, the last step is about AI, IA. Opposite of AI is IA, intelligence augmentation, where we combine computers, AIs, with our own minds to make our own minds stronger. Okay, now one of the key steps in there was off-policy learning and learning a model of the world. Off-policy learning means you want to be able to learn about things that you're not doing, or you're not, because are not doing all the way to completion. So even like to recognize an object, you look at the object and you say, how would you have to define that in some objective way. And the best way to do that is as a sub-problem. So yeah, maybe I'll just sort of stop there. The most interesting strategy, distinctive strategy of the Alberta Plan is that the mind works by posing sub-problems for itself and then working on them. And it's got a main problem, which is to get reward, but it also has many thousands of sub-problems it's also working on simultaneously. And since it's not behaving, it cannot behave for all 1,000 problems at once. It has to pick one problem, like perhaps the main problem, and behave according to that. And so all the other things have to be able to learn from data that's not exactly on what they would do. And this is called off-policy learning. And it's a key to learning to achieve auxiliary sub-problems. And also it's a key to efficiently learning a model of the world.
Yeah, you have something called the Horde architecture. Is that where that comes in when you break a problem down into multiple subtasks that you learn?
That was one paper where we worked on that idea. We developed that idea. The Horde is the horde of subproblems. Each daemon in the Horde, could be almost viewed like a single neuron in a neural network, is working towards a different task, trying to predict a different thing, or maybe trying to attain a different thing. It's the view of the mind as decentralized. There is one goal, and everything is ultimately driven towards one goal. But still, it's a useful structure to have different parts driving towards other goals.
How did you get together with John Carmack? Was that primarily because you need the funding and it gives you a vehicle to raise capital? No, seriously. I mean, you know, Jan LeCun's got Meta behind him.
Well, it's just not really comparable. John's company is great, but it's still like a $20 million company, and which is plenty of money for what we want to do now. John and I got together because we had similar ideas about what was needed, um, and also what was not needed to get to AI or AGI. Um, yeah, so I read a newspaper article, an interview that John did down in Texas, and I just could see that he was thinking about things the way I was, even though our backgrounds were quite different. He thought of intelligence, there's a few principles that needed to be worked out rather than, so it isn't a huge program to write. It's a few principles. We have to figure those out. Um, Not that many, maybe 10,000 lines instead of 10 million lines of code. So it's easy to get, it's relatively, it's still, it's still, it's still hard to get basic research funding in the world. It's easy to get funding towards applications of AI, large language models particularly. Um, anyway, I'm really enjoying working at Keen and being able to focus on the ideas. And it's a calm company. We um, there's a lot of thinking involved, a lot of contemplation. There is also experiments, and we're trying to get the engineering side of it is really important. But for me, it's been really great just to be able to
Yeah.
regroup my thoughts and think about them very carefully and push them forward.
But Keene is implementing the Alberta Plan. Is that right? I mean, that's the project.
Well, the Alberta Plan is a research plan. It's like a 5-year research plan. And so research is something you don't implement. Research is something you conduct. And it doesn't always end up the way you want. But um, yeah, I wouldn't say implement is the right word. Not yet.
But the work you're doing at Keene is informed by the Alberta.
Yeah, I'm working on the Alberta Plan.
And the end goal at Keene is to create the embodied intelligence described by the Alberta Plan. You don't sound very confident.
Well, a plan is just a plan, and I think there's a good chance it will work out as planned. But a 5-year plan, you make another one after 4 or 3 years. Um, yeah, so I wouldn't presume to know how it's going to work out. But at the same time, we have to make our bets. We have to think hard about it. Um, just knowing, we may well be right, but
your work is primarily in reinforcement learning. You wrote the book on reinforcement learning, temporal difference learning, and lambda, and all of that. Is this? I mean, this seems a much more ambitious project. Is this? Was it the success of the transformer scaling that said, well, let's do that with RL. Why are these guys? Everyone's celebrating what they're doing, but there's much more to be done. No.
So what you see in the Alberta Plan is perhaps bigger than the book, but this has always been the plan. We've always in AI tried to understand all of the mind and reproduce it in computers, and so that is a big, enormous ambition. That's what it's always been. So the large language models are a bit disappointing in some sense. I mean, it's really good that people are getting excited and people are wanting to learn about it, but it's not. I don't envision that it's the direction that will be most productive to pursue. Now, who knows? What I do know is it's not the most direction that's useful for me to pursue. I'm much more interested in actions and goals and how an agent can tell what's true and what's not true. All of those things are missing from large language models. So, no, they're not really. What they are doing that's important is they're showing what you can do with computation and networks and learning that you can get enormously complex things, and you can incorporate a lot of data. It just shows the power for those who needed to be shown that.
And it could be an
Mhm.
interface between humans and whatever you end up creating, the agents you end up creating. You still need a language interface to communicate.
Yeah, but I don't. I doubt that what we're doing with large language models today will contribute to that
Oh, is that right? Yeah. I mean, in other words, the
at all.
models that you want to build, the agents you want to build, would learn language as part of the learning process.
Yeah, so it's like we say, language
Yeah.
last. Language not language first. Large language models are language first. We just say large language last. Just as Jan LeCun says, we need to do rat level intelligence and then cat level intelligence, and we have to get those
Yeah.
figured out before we should try to make human level intelligence.
Where are you on the plan? I mean, you figured out reinforcement learning. You can build agents. You There are various architectures for creating representations from various kinds of sensory input, uh, and at that representation level, then you can plan efficiently. So where in all of that are you in your research?
Well, it's a little hard to explain non-technically, but you can say some things. Certainly, you can say that the various steps um, are not done entirely sequentially. You're always looking for areas of opportunity where you can make an increment of progress, and those could be, on step 10, or they could be on step 3. Um, but I could also try to be very rough and say that we're at about step 4 now. Um, we are still doing things where we're changing the basic underlying
Hmm.
fundamental reinforcement learning algorithms. Uh, we are not done with that. We need more efficient algorithms, and I'm excited about some of the changes, new ideas we're developing recently about how that can be done.
Can you talk about
Um,
those new ideas at all?
okay, well, one of the big things is efficient off-policy learning and the use of importance sampling. Importance sampling is where you see how likely you're to do things under your target and your behavior policies, and you adjust the returns based on the ratios of those two. And for a long time, I thought that was the only way to adjust the returns. But now the forward correction of the returns, I think, can be done um, by changing your expectations. So, like, if you're expecting a good thing to happen, you're expecting a good action to be taken, and then a different action was taken, a more exploratory action. So this is a deviation from your target policy, which would be more greedy. And one way to take into account the deviation from the target policy is to just say, oh, okay, now I've done something not best, so I'm just going to adjust my level. Now I'm going to expect a little less. And there's a systematic way of doing that. Um, that's gives us a new way to handle the off policiness of our returns. And so this gives a whole new family of algorithms. So that's exciting. Now, for exciting, maybe mostly for me, I think maybe the most accessible direction of excitement, of novelty, is in continual. So I'm going to say a bunch of things, and to me, they're all going to have the same solution: continual learning, meta learning, representation learning, learning to learn, learning how to generalize, how to construct a state representation, feature finding. That whole thing is coming, and it will be a kind of it's just a new kind of way, a new kind of way of doing learning in deep networks. Um, and I call it dynamic learning nets. See, dynamic learning nets have learning at 3 levels, whereas usually our neural networks only
Mhm.
learn at 1 level. They learn at the level of the weights. And in addition, we also want to learn at the level of step sizes. So all of Every place you have a weight in your network, you're also going to have a step size. So a step size is sometimes called a learning rate. It's much better to call it a step size because the learning rate will be influenced by many other things. So if we imagine a whole network, all these weights, next to each weight is a step size that is adjusted by an adaptive process that's adapted in a meta-learning way, a meta-gradient way, towards making the system learn better rather than just perform better at an instantaneous moment in time. Learning rates or step sizes don't affect the function. They don't affect the function implemented at a particular point in time. They don't affect what the network does. They affect what the network learns. And so if you can tune the step sizes, you also get learning to learn and learning to generalize well and things like that. The last element that we want to have be adaptive, weights, step sizes. The third one is the connection pattern. So who's connected to who? So this will be done by an accretive process of, like, let's say you start with a linear unit and it learns, say, a value function or a policy, and it does the best it can with the features available. And then it needs to induce the creation of new features because you need to learn a nonlinear function of your original signals. And so you need to create new features that become available to that linear unit. And in this way, you grow in a sort of organic way a system that can learn nonlinear functions. And so this is just a different way of ending up with a deep network that was all learned, including all the features. Dynamic learning.
Where is the data, the input data, coming from?
Well, the input data in reinforcement learning just comes from life, from doing things, seeing things.
Right.
There is no labeled data set. Yeah, maybe I should have said this from the very beginning. The whole idea of, I call it experiential AI, is that no one makes you data. You grow up as a baby and you play with things and you see things and you do things. And that's the data. And the trick of reinforcement learning is how do you turn that kind of data into something you can learn from and grow a mind from? So the beauty and the limitation of supervised learning is they say, well, let's not worry about that for now. Let's assume that somehow we have a data set with labeled things, and let's work on this subproblem. That's a great idea. Work on a subproblem, figure it out, and then move on to the next thing. But really, we have to move on to the next thing. We have to worry about how the data set, quote data set, is automatically created from the training information. There isn't ever a data set. Data set is such a misleading term. It suggests that it's easy to have this thing and store this thing and curate this thing. Really, life is full of, you do things happen, and then they're gone. Everything is fleeting. You don't have a record of it, and it would be enormously complex and not all that valuable to have a record of it. The feeling is totally different in reinforcement learning and supervised learning. And in particularly the way I would address it, many people do reinforcement learning by creating a buffer or a record of all the experiences that have been retained, that have been occurred at least for some period of time. And I think that's an appealing, but it's not where the answer is. The answer is embracing the fleeting nature of data and making the most of it when it happens, and then letting it go.
Well, that's why you want to make an embodied system so that you have all the five senses or more.
So you need, as you say, an embodied system, an interactive system that influences its input stream, its sensory stream, and that you get that interaction and for a long period of time. You can do this in simulation, or you can do it in robotics. I still don't know what's the best way, or if the best way is to do both, or maybe first one and then the other. John is interested in having learning from video, and he likes his view of the experience is you have massive numbers of video streams, like you're viewing 500 channels of television, and then you can switch to look at another one. Other people in Keene, my close colleague Joseph Modile, he's interested in robotics, and he thinks the best way to get an appropriate data stream is to actually build robotic hardware. Um, it's important that the world be large and complex because the worlds we want to address are large and complex. Um, and so you want things like video, and you want large data streams. Um, Now, you can use simulations to generate even video streams, simulated video. But inevitably, those simulated worlds are really quite simple. They have an underlying simplicity. They have objects, perhaps, in three-dimensional straight structure. Maybe they're rigid objects, and the vision is a very particular geometric form. They are generated, and they are made up worlds, and they are generated. So they're really, the worlds are less complex than the agent. Their goal would be to spend most of the computer power working on the mind, and just a little bit to create the simulated data. And that's the reverse of the way it really is, right? Every person maybe has a complex brain, but their world is much more complex, not just because the world consists of all these physics and matter, but it also consists of other minds, other brains, and other minds out there. And what goes on in their minds matters. And so the world is inherently vastly more complex than the agent. And we reverse that when we work on simulated worlds, which is always concerning. Anyway, those are some of the issues and the trade-offs between working with simulations or with physical worlds.
Nonetheless, you need to develop the architecture and the algorithms before you worry about the data stream, I would think.
Yeah, but you want to develop the right algorithms. And if you're working with a world that's not representative of your target world in an important way, it can be misleading. But you're right, and that's what we strive to do. I don't know if you know, but I think in my own work, it's almost always I want to focus on some issues, so I make a really simple instance of that issue, like a 5-state world, and I study the hell out of it, but I don't try to take advantage of its smallness. I study algorithms that are in some sense even simpler than the simple world, and I stress those algorithms and see what their abilities are. So we always, it's always part of research is we simplify the world, understand it fully. Just like a physicist might, make a simplified world with a ball rolling down a ramp, and it's a really simple world, and you try to eliminate the friction, and you eliminate other weird effects, and just see things in their simplest form.
Yeah. Have you paid much attention to Alex Kendall's work at Wave AI? Do you know that company? It's an autonomous driving company. They have a world model called Gaia 1, and it's similar to what Jan LeCun's doing. It encodes representations from video, from live video, and then plans based on those representations, and it can control a car from the representation space. It's actually pretty remarkable.
So let's talk about the world model, and what kind of world model would be appropriate for autonomous driving. So let me say some things that are mistakes, very natural seeming, but mistakes, in my opinion. The mistake would be to make a physics model of the world, or to try to make something that could simulate the world and produce the video frames. You don't want the video frames of the future. That's not the way you think. Instead, you think, oh, I could go to the market and maybe there would be strawberries. Okay, you're not creating a visual, a video. You're saying you're jumping to the market, and then your strawberries could be different sizes and positions, and still there's not a video. There's an idea that will happen if you go to the market. So people have realized this. Like Jan LeCun used to talk about generating video of the future, and then he realized it would be blurry, and now he realizes that you need to produce outcomes of your model that are not at all like video streams. They're not like observations at all. They're like constructed states that are the outcome of the action. Okay, so this is a very different from a partial differential equation model of the world, and it's very different from what self-driving car companies start with. Self-driving car companies start with physics and geometry and things that are calibrated by human understanding, engineers' understanding of the world and driving. But I suspect that's going to be what do I know? I'm not into self-driving. I don't do self-driving cars, but I know that like Tesla is and Elon Musk is, and so their goal is to make some. They started like everyone else with engineering models, but I think my understanding now is that they're building sort of more conceptual models that are based on artificial neural networks. Okay, and so rather than starting with geometry and understood things, they're just getting massive amounts of data and training it to make a model. We need a model that is at the level of high-level consequences, not at the level of low-level things like pixels and video. So one way you do that is by having state features that are at a more advanced level. You say, oh, this is a car, rather than this is a video frame. And basically it's as simple as you need abstraction in both state and time. Abstraction in state is like saying there will be strawberries when I get to the market, and abstraction in time is saying, oh, I can go to the market and then in 20 minutes I will be there, probably, and other things will be the same or related in natural ways. So we want to be able to think about, I could go to the market. You also want to think, oh, I could pick up the Coke can, I could move a finger, and that will have certain consequences. All these things that we know, you think are at vastly different scales. Going to the market is like 20 minutes. Taking a new job, might be a year. Deciding to study a topic also might be a period of time. We think and we analyze the consequences. Like you wanted to meet with me today, and we arranged it, we set it up. It was your planning took place over weeks and in some cases months, and we assembled the event of this interview by planning all that and exchanging high-level messages. All that, it's silly to think that that's done at the level of imagining videos that we might see with our eyes or audio signals that we might hear. Yeah, so we need models that are abstract in time and state. And as a reinforcement learning person, there's a particular set of technologies that I naturally turn towards to do that. The prediction is based on multi-step prediction by temporal difference learning. The planning is done by dynamic programming, essentially value iteration, but where the steps are not low-level actions, but they're called options. They're high-level ways of behaving that terminate. So there are things like going to the market, and they will terminate when you're at the market. So, at a certain conceptual level, it's clear where we want to go, to me, with abstract models in time and state, built with options and features. I don't know if we did write one paper recently, published in AI Journal, on the notion of planning using subproblems on the STOMP progression. STOMP means subtask, option, model, and planning. Put all those things together, and you can do the full progression from the data stream to abstract planning. And that's what we're trying to put together.
Yeah, and I sort of misspoke talking about Gaia 1 about that model. I mean, the input is video. It creates a representation, and it plans and takes action in the representation plans actions in the representation space, you can then decode that into video to see what it's doing, but you're not planning in the video space. So what's your ambition with this? You'll figure out to refine the algorithms, the reinforcement learning algorithms. They need to be scalable. Once you have that, then you move on and start scaling them with compute and following your roadmap, or am I simplifying it too much?
We want to understand how the mind works, and then we want to make a mind, or some minds, or some mind, amount of mind, and it will be useful in all the ways, in all sorts of ways. Economically useful. It'll also be useful to us to extend the capabilities of our own minds. If we can understand how our minds work, we can augment them so that they can work better. We're gonna. The key step is understanding, and then there would be millions of uses. I don't think it's going to be as simple as making workers sort of like slaves for us to direct. I don't think it'll be as simple as that. That maybe gives a lower bound on potential utility. Our story at Keen is we say that, if suppose you could make a virtual worker, this would be enormously useful. Much of the work that we all do from day to day doesn't require a physical presence. It doesn't require a robot. Much of which we do is just shuffling information around. We can do most things through a video interface. So why can't we make workers that are extremely useful by playing the roles that people play in many cases? That's sort of a lower bound on what can be done. I think much more can be done, and there'll be much more interesting things to be done. And then there's the question of what should be done. Those are rich philosophical questions and practical questions for the economy.
Yeah. I've seen your and one thing on reinforcement learning and sort of supervised learning sort of took over for a while. Now it's transformer-based generative AI, but during the supervised learning phase, the argument was that higher knowledge is all supervised learning, and
it's still supervised. It's still supervised. In generative AI, large language models, the training information is the next token, or the next word, and that's taken as the correct action.
The analogy you gave me was, because the analogy that's always given is that, a child sees an elephant, the mother says that's an elephant, and the child very quickly can generalize and recognize other elephants. Maybe it makes a mistake, and the mother corrects it and says, no, that's a cow. And that was always given as an example of supervised learning. But maybe it's reinforcement learning. Maybe it's the child's reward from the mother praising him for remembering the label.
The point is that a child has well-developed concepts before, and then when its mother says that is an elephant, there's already an extensive understanding on the child's part of what the space is, what the objects are, and the thing that is being labeled. No, the label is the least interesting part of that, and the child has already learned all the other most interesting parts of what it means to have animals and moving things and objects in its world. The label is the least interesting part of it.
Well, first of all, you were talking about agents that could be virtual workers. Already, using reinforcement learning, people are building agents and using large language models and knowledge bases to, you know, carry out tasks, knowledge-based tasks. Uh, so, what you're talking about is more than linguistic tasks or knowledge-based tasks. You're talking about physical planning and physical tasks. Is that right?
The key thing is having goals. And if you have, for example, an assistant help you plan your day, organize your day, or do tasks for you, I'm thinking it's very important that the system is able to have goals and is able to understand your goals. I think it's probably the most important part of an assistant is to understand the purposes involved. And large language models don't really understand the purposes involved. They will appear to a little bit, but the corner cases always come up, and once you spend a bit of time, you're always in a corner case. And so an AI system is a system that after a bit does silly things that don't respect the goals that you have or that have been given to it. That's not going to be a useful assistant. So I don't want to be critical of large language models. They're very, very useful, but it shouldn't be viewed as a criticism to say that they also at the same time have rather important limitations. It's not a competition in that sense.
Are you concerned at all? Or do you ascribe to the threat debate?
No, I think I think the doomers are they're not just wrong. I think they're blindingly biased. The bias is blinding them to what's going on. Basically, AI is a broadly applicable technology. It's not like nuclear weapons. It's not like bio weapons. It can be used for all kinds of things, and it's the way we deal with such things is we try to use them well, and there'll be people that use them for bad things, and then this is just normal. There's normal technology it can be used by good people or bad people. The doomers are just saying, oh, somehow it's going to be that it's bad in the same way that nuclear weapons are bad. And they're just blinded by that metaphor, by the thinking that the AI will be out to kill them. It's just silly, and I don't think. Well, the doomers don't actually give coherent reasons for what they believe, and so it's hard to argue with them. So maybe it's fair just to hold that they're biased and blind. I don't accept an argument unless it's a proper argument.
So where you say you're maybe at stage 4 in the research, Carmack says 2030. That's it's far enough out there that maybe people won't remember in 2030 that he said 2030. It's always
2030 has been out there for a long time, and you can't, it doesn't recede. It's always been 2030 for the computer power reaching human scale quantities. Yeah, but anyway, 2030 is a reasonable target for us understanding everything that we need in order to make a real mind. Yeah, I'm good with that.
Yeah.
You have to be ambitious. I've always said that 2030 is a 25% chance of achieving a real intelligence, a real human level intelligence. 25% chance, so probably not, but it's a big enough chunk of probability that an ambitious person should work towards it and try to make it true. And it does depend upon what we do, and not just the unfolding of the universe. So we should try to do that. That is the big thing that's happening right now is the public is coming to grips with what it means for there to be, for us to understand the mind and to have the ability to create minded things. And so that is a big transformation. It's a big change in our worldview, and so we absolutely need all kinds of people to help us become easy and have an understanding of what's happening as we achieve human level designed intelligence.
That's it for this week's episode. I want to thank Richard for his time. If you want to read a transcript of today's conversation, you can find one on our website, Eye on AI. That's EYE-ON.AI. In the meantime, remember, the singularity may be getting closer, but AI is already changing your world, so pay attention.